previous lessons in this series, we learned to calculate values using Boyle's law and then Charles' law. Now we're going to combine those laws together into what's called the combined gas law, and we'll learn to calculate pressure, volume, and temperature. So we're going to solve these problems in much the same way that we've done it with our previous couple of lessons. I'm going to give you an example and have you solve a few problems using this example in this manner, and then go on to another example and so forth. So let's start here. We're going to use the same system we've used for Charles' law and Boyle's law, where we first make a list of our knowns and unknowns. So we've got 2 liters of a gas. Well, that's a volume. So we're going to list volume as 2.00 liters. It's collected at 25 degrees C. Well, that's a temperature. So we've got a temperature at 25.0 degrees C. And then we've got pressure, 745.0 millimeters of mercury. That's what that symbol means, is a pressure. 745.0 millimeters of mercury. That's our pressure. And then we're going to say, what is the volume? That's a new volume. So the volume here must be volume 2 because we've already got a previous volume at STP. We don't know the volume here. STP stands for standard temperature and pressure. The standard temperature is 0.00 degrees C. You need to know that. If you don't have it memorized, you need to do that. So that's temperature 1 over here and temperature 2 here. And we've got a new pressure because standard pressure, STP means standard pressure. That's pressure 2. Standard pressure is 1.00 atmospheres, which it turns out is also 760.0 millimeters of mercury. Okay, so you need to know that standard pressure is 1 atmosphere and 760 millimeters of mercury. On the accompanying worksheet, you'll see those temperatures and pressures, standard temperature and pressure listed for you. Now, we know we have to convert our temperatures into Kelvin because none of these gas laws can be calculated using degrees C. We have to go to Kelvin. So let's convert the temperature in degrees C to Kelvin. We've got 25.0 degrees C. We're going to add 273.15 to that to get the Kelvin temperature. And we got 15 here, 892. So 298.15, that is Kelvin, but we've got a digit over there has to be rounded off. That 5, it comes from an empty slot here, so we've got to round it off. And we're going to get 298.2 K. And that's the temperature we're going to use and not this one. So let's list that as 298.2 K. We've got to do the same thing with this temperature, 0.00 degrees C. We're going to add 273.15 to that. And we get 273.15, and that's the Kelvin temperature. There are no empty slots over here, so this doesn't have to be rounded off. So we've got all our values here now, and now we're going to look at what the law is we're going to use. We're going to combine Charles' law and Boyle's law. So if you remember, Charles' law was volume 1 over temperature 1 equals volume 2 over temperature 2. And Boyle's law was pressure 1 times volume 1 equals pressure 2 times volume 2. If we put those together, the volumes, this volume 1 is the same as this volume 1. This volume 2 is the same as this volume 2. So we're going to just put it together then, and we get P1 V1 over T1. So you can see how we're putting that together. If V1 is the same here and here, then there's no reason to write V1 again. We just have P1 V1 over T1 equals P2 V2 over T2. And that's the combined gas law. And that fits the unknowns we have in this problem. P1 V1 T1 P2 V2 T2. So let's write our equation then. You always have to write out the equation where there's nothing put in there for any of the variables. So we're going to write P1 V1 over T1 equals P2 V2 over T2. Now we can plug in the values that we have to find the one we're looking for. So we know pressure 1, 745.0 millimeters of mercury. 745.0 millimeters of mercury. We know V1, 2.00 liters. We know T1 now in the right units, 298.2 K. And that equals P2, which is, we need to match the units here. The units of pressure is millimeters of mercury, so we need to use this version of our pressure 2, 760.0 millimeters of mercury. Let's see, we need V2 is what we're trying to find, so we're going to write times V2 here. And we're going to put it over T2, which is, we found it to be 273.15 K. All right. Now, if you remember when we were doing Boyle's law, we had to divide by whatever was next to our unknown to get rid of this. And when we were doing Charles' law, we had to multiply it by what was on the bottom of the fraction. We're basically doing the same thing, and we're doing both things to solve for this. The idea is we want to get this V2 all by itself. This is called isolation of the unknown. We're isolating the unknown here. To do that, we need to divide by this number and multiply by this number. And we've got to do the same thing to this side, because you've got to do the same thing to both sides to keep the equation equal. So let me show you how that works. 273.15 K goes on the top, and 760 millimeters of mercury, 760.0 millimeters of mercury, goes on the bottom. Okay? What I do to this side, I've also got to do to this side. So I'm going to write 273.15 K over 760.0 millimeters of mercury. All right? Now, this entire thing cancels here and here, because they're exactly the same. This entire thing cancels here and here. It's exactly the same. We're left with V2 all by its lonesome self over here, and that's how we've isolated the unknown. Over on this side of the equation, the Kelvin, or capital K units, cancel, and the millimeters of mercury cancel. We're left with liters. L stands for liters, and liters is a measurement of volume, so we know we probably successfully set this up correctly. So we're ready to do the math now. So we want to take and multiply this times this and times this, and then hit equals or enter, then divide by this, hit enter or equals again, and divide by this. So I hope you have this written down, and I can show you on the calculator how we're going to do that. If you need the substitute teacher to pause the video for a second for you to finish writing this down, ask her to do that. Now, we don't have a lot of time, so work quickly here. So let's go to the calculator now, and we're going to take 273.15, 273.15. We're going to multiply that by 745.0, and we're also going to multiply that by 2.00. Okay, and we're going to hit enter. Then we're going to divide by 760.0 millimeters of mercury, or 760.0, divided by 760.0, enter again, then divide by 298.2, and we get this answer. So 1.79583 liters equals V2. But we have to round off. I can look at this number and see that I've got 5 significant digits. All right, so, and I've got 4 significant digits. Here I've got 3 significant digits. Here I've got 4, and here I've got 4. So the measured number here in this problem that has the least digits is this 2.00, where I've got 3 significant digits. The 2 zeros after the decimal place are significant because trailing zeros in the presence of a decimal place are always significant. Non-zero digits like this 2 are also significant. So there's 3 significant digits here. We want to round off everything but our first 3 digits because these are the significant digits, these first 3, and these 3 digits are not significant. So we're going to round it off to 1.79, but that 5 is going to make the 9 round up to a 10, and that 1 carries over here to the 7, so we get 1.80 liters equals V2. And that's our final answer. Now, on your worksheet then, you're going to be solving a problem, several problems like this. So just like before, you're going to have one problem that's solved for you on the worksheet. And then you're going to have a problem that you're going to solve, and you'll find the solution to that problem on the back of the sheet. So you just go there and look and see if you've solved it properly. And then you'll have a couple of problems to solve that are not solved for you. So you have to just work it out for you. You can work with a partner as long as you work so diligently and reasonably quietly. If things get out of hand, the substitute teacher is going to tell you to stop working together and do it by yourself. So work diligently and quietly. Okay? You can whisper, talk quietly, that's fine. So that'll be the first 4 problems listed on your worksheet, and stop. Then I'll show you another example and we'll move on. All right, so let's move on now to the next problem. The previous problem was one in which we were trying to find a volume. And now we're just going to find the pressure. And this should be pretty simple. If you can find volume, pressure should be pretty easy to do too. But let's make our list of knowns and unknowns. We've got a volume of 197 liters at STP. Remember, STP... Remember, STP is standard temperature and pressure. I've listed them for you here, but you need to know what standard temperature and pressure are. 0 degrees C is standard temperature. 1 atmosphere, 1.00 atmosphere is standard pressure. That's what STP stands for. So we're going to list those now because our standard temperature and the temperature for this volume is 0.00 degrees C. The standard pressure and the pressure for this volume is 1.00 atmospheres. Okay? And then ask what pressure are we going to get when we do something else to it. So pressure 2, we don't know. Okay? We do know with that pressure we're going to have a volume. So that's volume 2, that's volume 1 over here then. Volume 2 must be 322 liters. And the temperature, our temperature 2 here, because we've got a temperature 1 here, temperature 2 is going to be 45.0 degrees C. Now, if you recall, when we determined the Kelvin temperature of a 0 degrees C value in our previous problem, that was 273.15. We could go ahead and write that here. And it turns out, and I said this yesterday in case you don't remember, that standard temperature is 0 degrees C, and it's also 273.15. So really, if you have 0 degrees C, you could just write it down 273.15 without showing the math to convert to Kelvin. But now this one's not at 0 degrees C, so you do have to show that work. So 45 degrees C, 45.0 degrees C, and we're going to add 273.15 to that. So 45.0 plus 273.15, and we get 318.15. So that's Kelvin. Now we do have an empty slot right here above this 5, and you have to round off that 5. So you have to underline to show that you're going to round it off. Underline that you show to show that you know that's an insignificant digit. Draw an arrow to show you're rounding off. That's the only operator that's allowed for showing you're rounding off, and it's required. 318.2K. That 5 we're going to round off makes the 1 round up to a 2. And so our temperature is this amount right here. Okay? That's the one we're going to use in the problem. Now we have volume, temperature, pressure, volume, temperature, pressure, and the only equation that works for that is the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And we plug in the values that we need, or we have, and solve for the one we're looking for. We're looking for P2 here. So plug in P1, that's 1 atmosphere. Plug in V1, 197 liters, over T1, and T1 is 273.15. We want to make sure we use the Kelvin temperature here, because you can't solve any gas law problems without the temperature being in Kelvin. And we're going to set that equal to P2, which is what we're looking for. So we're going to leave that as P2 times V2, 322 liters. And we're going to put that over temperature 2, which we need to make sure we use Kelvin for that, 318.2 Kelvin. And now to get P2 by itself, we've got to multiply by this and divide by that, and we do it in this manner. So this one goes on the top, this one goes on the bottom. And what we do to this side, we've also got to do to this side. So we're going to take that same fraction and multiply over here. And on the bottom, we're going to put 322 liters. And we're going to cancel everything we can cancel now. So 322 liters cancels here. 318.2K cancels here. And we're successfully have gotten P2 by itself, because that's what we're looking for. That's what we want to do. We're going to isolate that unknown. On this side, we're going to cancel out liters, because I've got one on the top, one on the bottom. You can cancel them like you can cancel x's and y's in algebra. Kelvin cancels for the same reason, and we're left with atmospheres. And atmospheres is a measure of pressure, so we know we've probably set it up properly. So if you've got this written down, I want to show you how to put this in the calculator. Okay, we've canceled all this over here. We're ready to put this in the calculator. So 318.2 times 1.00 times 197, and hit enter. Then I'm going to divide by 322, hit enter, and divide by 273.15. And this is the answer I'm going to get. So we're going to put that in there now. Actually, I should have written it down before I took it off the screen, because I don't have it memorized. So 0.712704, and that's atmospheres. And we need to round that off. I've got 3 digits here, 3 here, 4 here, 5 here, and 3 here. So the measured number in this problem with the least digits is 3. Leading zeros like this one are not significant. Trailing zeros are when there's a decimal place, but leading zeros are not significant. So there's our first significant digit, that's 7. 1, 2, 3. Underline starting at the 7 and 04. Draw an arrow to show a rounding off. That's what's required. And we get 0.71. That 7 makes this 2 round up to a 3 atmospheres, and that's equal to P2. And we're going to draw a box around our final answer so that when I grade it, I can tell what your final answer is if your solution isn't really clearly laid out. Okay, so again, there are some problems for you to do. There's one problem worked out for you. That should be number 5. And then number 6 is one that you're going to solve, and you'll find the solutions worked out for you on the back of the sheet. So go to number 6 to see, once you've solved number 6, see if you did it right. And then 7 and 8 are the more problems for you to do, for which I don't provide a solution, and you have to do that for yourself. And then you can work with a partner again, as long as you're quiet and as long as you work efficiently. But if you start texting on your phone or chatting or making noise, then the substitute teacher ought to let you know you have to stop and start working alone and be quiet. Okay, so do that, and then you can pause the video to go on and solve some of those problems. This is all timed because we've got certain segments of the class period laid out for you to do certain things, and then we'll come back and solve the next kind of problem and start the third set like we did previously. Okay, so now let's go on to the next problem here in our example problems, just like yesterday. Okay, this is where the temperature is the unknown. So the initial temperature of 1 liter of a sample. Now this is where, remember when we did in the Boyle's law, when temperature on the bottom, we had to end up flipping both sides? We're going to do that here too. So the temperature is the unknown. The initial temperature of a 1 liter sample of argon is 20 degrees C. So it doesn't tell us that temperature here, okay? But let's write down what we do know. We know that volume 1 is 1.00 liters. We know the temperature 1 is 20.0 degrees C. Then the pressure is decreased, okay, from 720 millimeters of mercury to 360 millimeters of mercury. Okay, so our pressure to start with then is 720 millimeters of mercury. And I didn't put a decimal place here, but let's put decimal places there and keep that 0 as being significant, okay? And so our new pressure is going to be 360 millimeters of mercury. It says the volume increases. So we went from 1 liter, we're going to go higher up to 2.4 liters, 2.14 liters. And then it asks what's the final temperature. So temperature 2 is the unknown. Okay? And don't forget, we've got to change this temperature into Kelvin before we move forward. The question doesn't ask you to change your temperature to degrees Celsius, so you don't have to at the end. If the question asks for degrees Celsius for the answer, you have to convert at the end. But for right now, we don't need that. But let's convert this into Kelvin because we've got to have our Kelvin temperature in order to do the problem. You can't put Celsius temperature into a gas law problem and get a correct answer. You've got to have Kelvin temperature. So let's take this, 20.0 degrees C, and add 273.15 to that. We get 293.2, actually 15 here. There's an empty slot above that 5. And that 5 is underlined because it's insignificant. And then we'll round it off to 293.2. And that's Kelvin. So this temperature here, 20 degrees C, is 293.2 K. Okay, and that's the one we want to use in the problem. Now then, let's set up our problem. We have V1, T1, P1, V2, T2, P2, and that equation that will be used to solve this is the combined gas law, P1, V1 over T1 equals P2, V2 over T2. And we're going to plug in what we know. We're going to plug in 1.00 liters for the volume. Well, I guess I should put pressure 1. You could do it this way, but let's do it the way it's listed here. It really doesn't matter if we reverse pressure and volume, but I want to do it the way it's shown here so I won't confuse you guys. Then, so we're going to say P1 is 720 decimal place millimeters of mercury times V1 is 1 liter. And then on the bottom of that is T1, which is 293.2 K. Over on the other side, we have P2, which is 360 decimal place millimeters of mercury, times V2, 2.14 liters, over T2, because we don't know what that's going to be. All right. Now, since T2 is on the bottom, we've got to flip both sides. Okay? Don't forget that when an unknown is on the bottom, you've got to flip both sides. I'm going to write it a little bit smaller so I'll have room on this ends over here to do the isolation step. So T2 goes on the top over here. I'm going to put 360 decimal place millimeters of mercury times 2.14 liters. Over on the other side, I've got to flip both sides. I've got to flip this side too. What I do to one side, I've got to do to the other. So this side has to be flipped as well. So 293.2 Kelvin has to go on the top. 720 decimal place millimeters of mercury goes on the bottom. As does the 1 liter. All right. Now then, this is on the bottom. And just as when we're solving Charles law problems, we've got to multiply by what's on the bottom here on both sides. So this is just two things. You can treat it like one thing. But both of these have to go on the top to be able to cancel them out and leave T2 by itself. So we've got 360 decimal place millimeters of mercury times 2.14 liters. And that goes over 1. Over on the other side, whatever we do to this side, we've got to do to this side. So all of this has to be put over here as well. Okay, so what we did to one side, we did to the other, and now we're ready to cancel the things we can cancel. Well, all of this on the bottom here is the same as all of this on the top here. So this cancels that, and that cancels that. And we've got T2 by itself. On the other side, millimeters of mercury can be canceled, and liters can be canceled. And we're left with Kelvin, which is a measurement of temperature, so we know we probably set it up right. And we're ready to do the math. So make sure you've got this written down on paper, and we can then show how we're going to put that into the calculator. All right, so let me clear out what I've got on here now so you can see what I'm working on. All right, so we've got 360 decimal place times 293.2 and hit enter. Then we're going to divide by the first thing on the bottom, 720 decimal place. Hit enter. And then we're going to divide by the second thing on the bottom, which it turns out division by 1 gives you the same answer, but that's fine. I'd just follow the process if it were me, and I was first learning this sort of thing. So our answer then is 146.6. And we'll go back now to the sheet we're working on, 146.6. The units of measurement we have left are kelvins. And then we want to look at our significant digits. I've got 3 significant digits here. Putting that decimal place right there, let's see, let's show it right here. That decimal place right there, that makes that 0 significant. In the presence of a decimal place, trailing zeros become significant. When there's no decimal place, trailing zeros are not significant. But this is going to be a significant 0. That's 3 significant digits, 4 significant digits, 3 significant digits here, and 3 here. And these 2 zeros are also significant because they're trailing zeros where there's a decimal place present. So our least number of digits in this multiplication division problem is 3. We want 3 digits in our final answer. So we're going to underline this 6 because that's our first 3 digits there. Those are our significant digits. Draw an arrow to show a rounding off, and write our answer as 140. That 6 makes this 6 a 7 Kelvin equals T2. So there's our answer. Okay, again, you're going to be solving these problems you've got 3 problems. Actually, you've got 4, one solved for you. Then you've got a problem that you're going to try to do for yourself, and you can look on the back of the sheet to see the solution, to see if you did it right. And then you've got a couple problems for which there is no solution provided, and you'll work on those. And then when all that's done, you've got a couple more problems to do on the worksheet. Now, if you get it all done during class, great, you're done. If you don't get it all during class, you're going to have to do some more work at home. This worksheet has to be completed by tomorrow. So, one last thing to show you that really has nothing to do with this problem. We did talk about having to convert back to Celsius. I showed you an example of that previously, but I'm going to show you that now. Suppose we take this answer here, and suppose that this question asks for the answer in degrees C. We have it in Kelvin, 1 at degree C. That's what I have here. It says, what is the final Celsius temperature of the gas in the last problem? The last problem, we left it in Kelvin. Now we're going to convert it to Celsius. So if you need your temperature in Celsius and you have it in Kelvin, the way you do that is you take 147 Kelvin and you subtract 273.15. So if you're trying to go from Celsius to Kelvin, you add 273.15, but in this case we're going from Kelvin back to Celsius, so we're subtracting 273.15. And so let's show how that looks in the calculator. So 147 minus 273.15, and we get a negative 126.15. And so that is degrees C. Okay? We're subtracting 273.15 from the Kelvin temperature to get the Celsius temperature. Now we've got 2 empty slots above this 1 and this 5. So these 2 digits here get rounded off. We show an arrow when we round off. Don't forget your negative here. This is a negative 126 degrees C. That's our final answer for the temperature, the second temperature in degrees C. All right, so again, you got those problems to do. Finish the worksheet.